piece into the octagon directly inside. Okay. Oh, you mean this is so the functions has already appeared in the octagon.
Yeah, that's right.
I can, if I enter all of them, and when I enter it, it will get result. Oh, I think so. So everybody will get the same result.
When?
And in question 1, type B and type C. So everybody should get the same.
Well, I used to know how to do
Cool. So that'll be a good place to start. Maybe I'll do some
Okay, so let's get started. So we're going to be doing the last lecture today on kind of this extended section that kind of mixed together ideas from like regression and also dimensionality reduction. So we're talking about this section on some matrix sketching, and this will basically be looking at things like the SVD, but trying to show how to do them at larger scale or increasing the interpretability of these. After this, we're kind of trying to round out the end of the semester. So we're going to have a week where we talk about kind of noise and cross-validation and outliers and privacy issues, and these are all going to these lectures, the next two after this will be a bit more, they're going to be less about kind of here's another cool technique to analyze data, and be a bit more like the lectures themselves will kind of be like the discussions on like the ethical use of some of these techniques we had earlier. I may or may not label them technically an ethics thing or something like that, but they'll have at least some flavor to that as well in the next week. And then the last section will be on like the analysis of graphs. And so there'll be one final homework. Again, this will be roughly half homework, like the frequent items homework. So this will be smaller. It'll be due. I think this is technically after this the after classes end and so forth. But this one shouldn't take too long. Final report's coming up. Hopefully you're all getting some good feedback so far, and some of you will meet with me after class today. Again, we have these 5-minute meetings because I think on average, I guess it turns out they're taking about 7 minutes instead of 5 minutes. But if you want more time, feel free to come up to me like any other day after class or in office hours, or send me email and I can give you more feedback on your project. I'm always happy to do that. Okay. And then one of the things we'll talk about today will make up one of the questions for this homework. So you'll be mainly have the material to do. We'll talk about cross-validation, which will have to do with one question on Monday then. So if people are really, if this homework you're like, oh, we didn't have enough time to do it, I might be willing to push it back a little bit, but if you guys are okay with this deadline, I'd rather, if this isn't too busy a time and you'd rather get it done, then I'm happy to keep the deadline where it is. Okay. Okay, so let's get into the lecture. So we're talking about so matrix sketching, and the numbers are mixed up. They should get back on track after this lecture. Okay. So the goal here is kind of looking at this singular value decomposition, which was very essential for a lot of these analysis techniques for dimensional reduction. We saw a few weeks ago. If you remember, you've got this large matrix A right here, right? Which and so it's got n columns. So n columns which are going down this way, and d of these, or n rows. Seeing if you're all still paying attention early on in this lecture. And d of the columns here, right? And so we're decomposing it as the product of these three matrices. And these three matrices are bigger than the original matrix, so that seems kind of wasteful, but they capture lots of information. One way to look at it is this matrix S. Most of it is zeros. This part here is all zeros, and this is all zeros, and that's all zeros. So, you know, it's actually much sparser, which means that this part of U, which is not all zeros, is kind of meaningless because it's always multiplied by that gray zone of zeros. And so then the resulting values along the diagonal of the S matrix are called the singular values, tell how important some direction is. And then these rows of V transpose, or the columns of V, are the right singular vectors. And in the d-dimensional space, which you can think of like the space of the attributes of your data, where each row is a data point, these tell you the important directions in this high-dimensional space. They're scored by these singular values in the S matrix, and they're orthogonal to each other, so they provide a basis. So you can take the top, the top k of them, the top, say, 2 of them, and that tells you the best two-dimensional space that represents the data, considering this forces it to go through the origin of that space. But you could, with PCA, you can kind of lift it off the origin. All right, so just review of, so then this is the best rank k approximation. You just add more zeros here, and then you become, you know, then this part is uninteresting, this part's uninteresting, and this part too, and you really compress the representation. Okay, so this is a review of kind of the SVD approach, and so this is used heavily to kind of pre-process data and inside a lot of other routines. And so if this has n rows and d columns, then this is going to take O of n d squared time to compute this decomposition. And while there are some approaches that try and specialize this for these like high performance computing, these big cluster machines, not the typical ones for data mining, data analysis we'll start talking about in a couple of weeks. This typically needs, like, in order to compute this, the typical techniques require that it stores this entire matrix and the output on a single computer, basically in the memory of the computer at the same time. And so when n and d both get especially large, and this is when n is usually larger than d, like in this picture, when these are especially large, this can be painful to compute. And this can be kind of, you'd often like to do it faster than the amount of time it takes to do this. Closer to the time it takes just to read through the data. Right, so we'd like to get something like this, but without having to spend this extra time and this memory-intensive approach. And so we won't be doing anything too large in this course, just not to make it too painful for you at this point in the semester. But like, if you try and run this on a very large data set in MATLAB, at some point your computer will say this is too big. So we're going to talk about an approach today that is going to allow you to do this in a much smaller amount of time. So the amount of time it takes to write down the relevant part of this solution is going to be like this part here, kind of along here, and this part here. This takes, this is n times k space. This is, and this is k times d space. So if k is much less than d, then this is much smaller than the original matrix, right? So if often this might be, let's say this is 10, and the original d might be something like, could be 10,000 attributes that you have in your data, and you could have millions and millions of these records. Then this can be a smaller representation, and so we're going to look at things that have runtime that's going to be closer to n times d, which is the time it takes just to read the data, times a factor of k, and k can be often much smaller. These will, is going to somehow approximate the solution to the SVD. So it's not going to give you the exact best solution, but it's going to give you something that's pretty close. These have been discovered only fairly recently, whereas the SVD has been around. People have been using it a lot for like 50 years, but the algorithms have focused on like 10 digits of precision in the accuracy. Often for analysis, you need like only like 2 digits of precision. So you can deal with a fair amount more of approximation and to get a much faster runtime. These also work in a streaming setting. So as the rows are coming in one at a time, so if you think of now as A1, A2, up to AN, where AI is a row of A, right? I'm reading through this matrix from top to bottom, either off of disk, or it's coming in. I'm getting new data points all the time. I want to maintain an estimate of the SVD as the data is streaming in, and not have to kind of update it every time I get one new data point. These algorithms we'll talk about will also work in a stream, so we'll be easily able to update these as new data comes in. So these are kind of modern approaches to kind of applying this onto much larger data sets. Okay? So I'm first going to talk about a simple approach that's also going to add another nice advantage that it's going to make it more easily to interpret what's going on, right? So let's say that I use, so if I use the SVD in, say, inside PCA, what I end up doing is I take high-dimensional data, right? So I have data here that's in RD, and I map it down to, say, R2, and so then I can draw this picture. Was hard to understand what's going on. I can't draw it in the original space. Now I can draw it over here, and maybe I see that there are some clusters. But what I don't understand, where before these may, the dimensions of the d-dimensional space may have correspond with day 1, day 2, day 3, and some sequence of readings I get. For instance, I took the weather for 100, the temperature at 100 consecutive days, or maybe 365 days in a year, and I'm comparing these across different weather stations, right? But when I project them, this is then just, say, V1 and V2. I don't really know what these dimensions mean anymore. All right, so if I want to do this, I want to reduce the dimensionality down, but retain the interpretability of the axes here. This would be something that would be useful. Here I understand what the coordinates mean in the original data set. I don't once I do the singular value decomposition or PCA anymore. Right, so I'd like to do something where it looks like this singular value decomposition, like this, but but when I project down to the basis I get is interpretable. I know the meaning of these basis vectors, right? So I could say this dimension corresponded with one of the days or something like that. Right now, what V1 means is something like alpha 1, let's call this x1 plus alpha 2 x2 and plus alpha d xd, right? So if I d coordinates x1, x2, and up through xd, the original d coordinates, it's a weighted linear combination of these, where alpha j is going to turn out is v1 dot product xj. Right, so if I took the dot product with v1, I get this weight, and it's a weighted linear combination of these, and it's usually, and all of these are going to be non-zero in the typical sense. Right, so I can say, well, this means some linear combination of these, but this really isn't that helpful. It's often kind of fairly evenly distributed among a bunch of these. So there's not a good interpretation of what's going on here. All right, so how would we create a basis that's more interpretable than these kind of linear combination that I magically get out of an SVD? Yeah.
You could hold like one dimension constant, and so you would have an intuition about that one, I guess. I don't know if that makes any sense. And then scale it down, but keep that one holding that.
So hold one of the dimensions. Do you mean one of the original dimensions over
Yeah,
here?
so if you have 30, you hold one of them, or like however many you want to keep, and then try to scale it down with just that one dimension.
Yeah. Okay, so I could pick, so what you're suggesting is I could pick this one as being xj, and then this one as being v1 of my data set that's minus the projection onto xj of the data set, right? So this is the first singular vector of everything not in this direction, right? So I get one direction that's interpretable and another direction that's not, but it kind of captures what the variation is in general. Yeah, so this is an interesting idea. You know, I know people do stuff in Viz where they look at a lot of combinations of the original dimensions. I haven't seen someone do this. This might be an interesting idea of how to understand individual dimensions. I know there are some Viz graduate students here maybe. This might be interesting. I don't know. This wasn't what I had in mind though. But what I did have in mind is keeping one of these directions constant, right? Your point is, if I choose one of the original coordinates, this is interpretable, right? Yeah.
Does it involve some kind of linear combination of that constant dimension?
Well, so I'm thinking, I know if I choose the original coordinates, these are interpretable, so how good can I do by choosing the original coordinates? So instead of saying each principal component is going to be a linear combination of all the coordinates, I say, I'm going to project it down and try and capture as much of the information as possible. But I'm going to enforce that each of my new coordinates is going to be just one of the original coordinates. So I'm just going to ignore, you can think of ignoring some of the coordinates or just selecting some of the most informative coordinates. Okay, so I like to do it where I project down to maybe not 2 dimensions, but a smaller number of dimensions. So I'm going to go to say Rk using K original dimensions. Okay, so I might not be able to go down far enough where I can plot it, or maybe I can pick the 2 most informative ones and plot it. But if I can just write down, these are the 5 or 10 most informative coordinates that really capture the variation. Let's ignore the other 90 or 990 of the dimensions that I have. And say, just look at these. These capture what's going on. So I'm going to try and do this. Yeah.
But I mean, using previous knowledge, we can know which are those K dimensions, or how do we know how to select those?
Yeah, so I'm going to tell you how you can select a good set and how well this works.
Okay.
Right. So I'm just motivating what we're going to do, and then I'll tell you how to do it. Okay. And okay. So there's some version of this which is like the orthogonal matching pursuit kind of algorithm we talked about, where you just pick the most informative direction, and we were doing that for trying to fit fit linear regression instead. But in this case, we're going to try and choose the dimensions to fill out a basis. Instead here. So we're going to pick the one coordinate in the original space up here that has the most variation alignment. Okay, and then if we're doing something like orthogonal matching pursuit, we kind of factor out that variation and we pick the next most informative direction. So in practice, I'll tell you what's most commonly studied and done at a very large scale in practice, and that's something even simpler than what we had before. So let's call the rows, or so often people talk this as, so we're going to be selecting the columns. So we'll say the columns of A are going to be C1, C2, up to CD. And I'm going to give each column CI, let's go CJ, a weight WJ, which is just going to be the norm of CJ, right? So if I have a matrix A, this is A here, then this column is CJ. Right? I'm going to look at the squared norm. Okay, so I'm going to look at that column, all the entries in it, and I'm going to look at the squared norm of this column. Okay, so I'm just going to, for each of the elements in it, I'm going to square the elements, I'm going to add those up. That's the squared norm. Okay, so this is equal to the sum over I equals 1 to n of aij squared. That's what that's equals to. Okay? And now I'm going to select a set C, which is going to be C 1 prime, C 2 prime, up to C k prime, where each Cj prime is going to be chosen at random proportionally to this weight, right? So if the weight is if I have two columns and one weight is twice as big as the other one, I'm twice as likely to select that column with the larger weight. Right, and we had talked earlier in the semester about how to do this. If you think about, you have all of these columns and they have different weights to them. So this is weight 1, weight 2, weight 3, weight 4, and weight 5. Right, I can take the weights and scale them so that they fit between 0 and 1, and then I can choose some random value uniform between 0 and 1, and it's going to fall somewhere along here, and it's whichever bucket it falls into, this is going to correspond with weight 2, which is going to correspond with column 2. Right, and I'm going to do all of these IID. So I'm going to do them all these independently. Okay, and so I'm going to choose k columns this way. And so this is a fairly common algorithm of how to do this. Yeah.
So you're picking the weights by calculating the norm, but it doesn't, how does that tell you the variance? That just tells you how, what the magnitude of all the points are.
Yeah. Okay, so this is not exactly the variance if you centered the data first. So every column had an average value of 0, then it's the variance. So if I'm doing the PCA version of this, then I can pre-center all the columns, and then I do this, and that's exactly the variance. It turns out for the SVD, which is slightly different than PCA, then this is the thing that corresponds with variance in the same way. And this is the thing that optimizes the selection with respect to the SVD's problem. So if I want to do something that's trying to approximate the mass I capture the way the SVD does, then you should select with the squared norm. But if you want to do it like PCA, you should center them first. That's a good point. Yeah.
So should the sum of the weights equal to 1?
Yeah, so I can normalize them. I can normalize them first if I do this. If not, if the sum of the weights is equal to, say, 300, right? So it goes from 0 to 300, the sum of them. Then I can take a uniform value and I can multiply it by 300. And then I place it somewhere between 0 and 300, and it works the same way. Yeah. So you have to kind of, this is one way of doing it. Okay, so this is kind of the whole algorithm of how to do this. This gives me a, I'll tell you a bit faster way or a streaming way to do this, and I'll tell you a little bit about the properties of this algorithm. Basically, I'm going to need you need k to be you want this to be roughly, I'm going to put, I'm going to say k prime here over epsilon squared log 1 over delta. And so k prime is the rank of the matrix you would like to approximate. So if I'd like to get a k prime dimensional subspace, then I basically need an extra 1 over epsilon squared factor. Right? So if I want to capture something within roughly 10%, and I'll write that down on the next slide more formally, then I'm going to need an extra 100 times that number of columns in theory, right, with an extra log 1 over delta for probability of failure bound like this. So this works, the way to interpret this is it works roughly as well as the random projection technique that I talked about on Monday. And it's not going to work as well as doing the kind of the SVD in memory. These numbers mean that this again only is going to be useful when I'm at very large scales, right? I'm not going to be doing this to project down to 2 dimensions. I'm going to be doing this to go from, say, 10,000 dimensions down to 500 dimensions, right? That's roughly at the scale where this sort of stuff is going to work. Now, in machine learning and various places, you occasionally will get that many different features, and you want to reduce it down to 500, and this is a reasonable thing to do. So when you get to these massive things where you're generating huge numbers of potential features, then this is a way that you can select them. Okay, if you care about something with a much smaller number of them, then you're going to do something kind of more complicated like the orthogonal matching pursuit approach, where you select the single most informative of these at a time. I'll tell you a little bit more about that in the next couple of minutes. Okay. So, but this is called the columns subset selection technique or problem, and this works roughly as well as the most commonly used versions of this, which are a little bit more complicated. But you might as well just do this. Okay, I want to mention, I forget, did we talk about, so in the streaming part of the class, did we talk about reservoir sampling at all? Okay, so this is I just want to spend some time on this. This is a really cool streaming technique. So I'm going to, I have a stream, say A1, A2, up to AN, and each of them is going to have a weight associated with it. And so these can be, N can be D, these can be columns. I can be seeing the columns one column at a time. I have a bunch of data points and I get a new attribute for every data point I'm seeing over time. I'm measuring something at N different locations for like over time. Right, so I'm going to get a weight next to these things. And let me initially say that each of the weights is going to be this, each weight J is going to just be constant for now. I'll fix this. First, let's assume the weights are constant. Okay, what I want to do is I want to, as I go through this stream, which means that I see the first thing in the stream, then the second, then the third, and I can't store them all in memory. I want to maintain a random sample, right? And I'm just going to maintain one point at random, chosen at random from the stream. If I want to maintain k random samples, I do this k times in parallel. So I might pick something twice. But there are ways to do it where you don't pick something, you enforce you don't pick something twice. Those are a bit more complicated. It usually doesn't buy you too much extra, although it helps a little bit. Okay, so I'm just going to maintain one of these things at random. Okay, so I'm going to say R is going to be a random point from AI, right? Which is the stream A1, A2, up to AI. So I stop after, so this is partway through the stream. I pick one random point. At any point in the stream, I want this to be uniform at random. It can be done proportional to the weights too. And I'll come, so, but for now, if they're all equal weights, then I just want a uniform point at random from the stream. Okay, and there's a simple method way how to do this. Okay, so so this is for AI, and I'm going to have an algorithm which is going to work in like an inductive sense. So so I have to maintain the value of number of things I've seen so far, which is I, and now I'm going to say with probability 1 over I plus 1, replace R with AI plus 1. Otherwise, keep R equals R. So I keep what the old sample was. Okay, so at the base case of the stream, the first thing in the stream, I set that as R. And then the second thing in the stream, that's going to be, I is going to be equal to 2. Then I'm going to replace R with A2 with probability I plus 1 is going to be equal to 2. Right? So I'm going to replace it with probably 1/2. I'm going to replace it with A2. Otherwise, with probably 1/2, I keep it as A1. Then the third thing comes along. So I plus 1 is going to be 3. So with probably 1/3, I replace R with A3. Otherwise, I keep it whatever it was before, either A1 or A2. Okay? And so you can show, so the probability of replacing it with the new thing keeps decreasing, by, it's always 1 over the index of the item I see. And this guarantees that whatever I keep in the counter is uniform, is a uniform random sample from everything I've seen so far.
So you said that at I equals 2, you're gonna, so probability 1/3, you're gonna replace it with that probability with A4?
This is kind of, I didn't plan this very well, but this is, so think of this as step I plus 1, right? So if I plus 1 is equal to 2. So after AI is A1, so this is what I've seen so far, right? And then so if this is A2, then I've seen the first two things, and I plus 1 is equal to 3.
And it's a stream, and it's just for that one point. And
So I just do it just for one point. Yeah.
So this seems like it makes you assume that the first things you see are correct and the things that you see later are incorrect, or am I not understanding this concept?
So it's not as like correct or incorrect. I just want to maintain a random representative from the stream. Or if I want to maintain 10 random representations, I do 10 of the same algorithm with different random process in parallel. So then I have R1 through R10, I maintain them by the same process.
Okay, so this works best when you have multiple Rs, multiple random samples.
Yeah, right. For instance, in this algorithm here, I did this k times, where k is 500. So I do 500 columns I'm going to keep at random out of 10,000, something like that. Right, so I'm going to see 10,000 columns. I'm going to maintain 500 at random. Initially, all 500 estimates are the first column. Right, so this isn't that useful. Maybe I front load the first 500 columns are fixed as the different counters, and then I replace each of them independently.
Would it make sense to randomize your stream for different Rs? Or is that?
So this assumes the order of the stream is adversarial. It could be anything, but this is going to guarantee that what I keep is going to be a uniform random sample independent of what the order was. Right? So it's not biasing towards the things at the front of the stream or the things at the end of the stream. So if you think about it, if I look at the 10th item in the stream, and after I've processed that 10th item, what's the probability I should have kept that as my representative? 1/10, right? And when I see it, the probability, if it's I plus 1 is 10, the probability I keep it is 1/10. Right? So for that item, it makes sense. For the last item I saw, I kept it with the right probability. Right? If I see the 11th item, then there's some probability that it's been replaced. Right? And there's some probability that but most of the time I didn't keep that one. I didn't keep that item anyways. So the probability that it's been replaced, it drops down to only having been kept 1 out of 11 times. I've only siphoned off a small amount of it. So I'm like the analysis isn't too hard. I'm not going to go through it, but there's kind of a couple line proofs out there. You can also adjust it for the weight. Instead of keeping it with 1 over I plus 1, I keep track of the total weight I've seen so far, and I keep it with each item with the correct weight at the time I saw it. And everything that it keeps track of all the previous weights kind of automatically. So I can maintain a random sample in a stream easily, which means that I can run this algorithm in a stream as if I see the columns one at a time. Okay. Okay, let me say something about what you can say about the error bounds of this. So if I have I've got written down for projecting rows, but I think I'm going to get this right. So if I say C is going to be C1 prime, C2 prime, up to CK prime, right? So I'm going to put the columns I kept next to each other into a column matrix. Then I'm going to define a projection matrix. And I think the right way to define this is hopefully I'm going to get this right, is going to be C transpose C inverse C transpose. And so then what I can do is, if I do the projection matrix times A, then this is projecting, this keeps, the result of this is still going to be a matrix that lives in, it's still going to be an n by d matrix, but it's going to live on the subspace that spans C. Think of, I'm multiplying, if I look at what this projection is doing, I'm multiplying by C transpose and then back by C again. So I'm kind of undoing the operation of multiplying by C. And the C transpose C inverse is kind of removing the norm that the scaling part, I've done that. I'm undoing the scaling by doing that inverse thing in the middle. So I can normalize stuff first and get rid of this, but this is projecting onto the subspace spanned by these columns. Okay, and this is interesting because this kind of works as like projecting onto the best rank K subspace. Now I'm projecting onto I want to project onto the best rank K prime subspace, and I'm projecting onto a K which is larger than K prime. And so I can say that A minus this projection matrix A, the Frobenius norm of this is going to be less than A minus a K prime, which is the best K prime dimensional subspace, or rank K subspace, times epsilon times the Frobenius norm. So I'm going to have some, so I set K to be K prime over epsilon squared roughly, like an extra 100 factor. And I'm going to say that the error I get for this projection is going to be less than the optimal error, plus some small additive factor here. And so there are some bounds that you can claim theoretically that you're going to get some guarantees on this, and that's where the k equals roughly k prime over epsilon squared. This comes from. Okay, so you can formally state some bound like this. There's a way to get a relative error bound, but to do that, you roughly need to compute something like the SVD first. And then you can change the sampling probabilities to be a little bit more intelligent, but it's a much more complicated process. You could also think about computing one of the columns, projecting, looking at the remaining error by doing this projection operation with just the column that you've picked, and then rescaling the remaining columns in here based on their weight, and then sampling according to that. That's going to be like a k-means plus plus version of this, and this will adapt so you don't pick two things that are pointing in the same direction as likely. So you could think of doing it like that, but you can't really do that in a stream. So people often don't discuss this sort of approach. But that would be more data adaptive. Or you could pick the one that has the maximum norm after projecting stuff out. But that actually works reasonably well. Okay, so this is an approach that gives you something that can be more scalable at very, very large sizes, and it gives you something that could be more interpretable than the regular PCA. Okay, any questions about this? I'm going to move on to another matrix sketching approach. Yeah?
So can you go back just one slide? So what if you just, this is just a thought experiment, but what if you just had a consistent probability of replacement? Would that ruin this?
Yeah, so what's going to happen is you're going to bias towards the things you saw more recently. Right? The thing you saw at the very beginning, you picked with, you put the first thing in, the second thing you kept with probably 1/10, right? And then, and that means every time after that, 10% of the time you threw that item away, even if you did kept it the first time. So the second thing you put in there, the probability of keeping it goes down to 0 exponentially. Yeah, so you're gonna, the things early, and so if you want to bias towards more recent things in the stream, then this is a common thing to do. But if you want to have it uniform over everything you've seen because you think they're all equally important, then this is the right way of doing it.
So one question. I think I didn't understand. Can we find meaningful dimensions if we are to plot in 2 dimensions? Only in 2 dimensions?
So there are cases where you basically can't, where PCA will capture almost everything, and doing something like this will do horribly. I can show you not too complicated construction after class. But sometimes this works okay. Sometimes there are 2 really informative dimensions. And you don't know until you try. Yeah. Yeah.
Is there would it be any better if instead of inverse relationship, we made it like exponential? Like.
Yeah, then what's going to happen is you're going to bias towards a thing at the start of the stream.
Okay, so this is like the sweet spot.
This is just the sweet spot, just the right way to do it. This is kind of like one of these gems of an algorithm, that this works just right. Yeah. So just pick the item with the proportion that you want to keep it, considering that this is the end of the stream. And then basically, by induction, everything works. Okay, so let me talk about a different approach now that's going to work considerably much better in practice and works in a stream. Not quite as well as the actual SVD, but it's going to come much closer to it. You can project down to roughly the same scales as you could with the singular value decomposition, This is going to be called the frequent directions algorithm, and it's kind of going to be like a matrix version of the Misch-Gries algorithm for frequent items. Remember the frequent items thing? I had a bunch of these counters, right? And if I saw a new item, either I could just add it onto a counter, or if it was a new item, then I removed one from each of the counters. And then if that creates an empty slot, then I can put the next one in that empty slot. Right? This was the Misch-Gries algorithm. And this it was kind of a very simple thing, but it had as strong guarantees as you can get for the frequent items in the string. So this is going to do something that kind of replicates this in a matrix, but kind of you need to kind of think through the linear algebra instead. Okay, so what it's going to do, now I'm going to be thinking about the stream is going to be the rows. So A, A1, A2, and so forth, where AI is now going to be a row of A. So AI is going to be in RD. AI. And so this is going to be N by D. And I'm going to be maintaining a matrix that's going to be, I'm going to use notation, so it's going to be 2L by D. So L is going to be something like the rank K. K and L are roughly going to be on the same scale. Eventually I'm going to set L equals to be K over epsilon. So I'm going to have, instead of an epsilon squared factor, I'm going to have an epsilon factor. And so I'm going to have this other, so this is going to be a matrix B, and this is going to be a matrix A. And so I'm going to have a much smaller matrix, it's going to have a smaller number of rows, but it's going to have the same kind of right singular vectors and singular values as A. And I'll define what that means, the formal guarantees, after I tell you what the algorithm is. Okay, so I'm going to have a matrix B, which is going to be much smaller, and I'm going to say this in B. I'm going to maintain the invariant that B has at least one all zeros row. So this last row here, I'm going to keep as all zeros. And this is just going to be for kind of bookkeeping. So there are 2L rows, but really 2L minus 1 data rows. And so this means if I see a new row, AI, I can initially load it into one of these rows that's all zeros. I can throw away the zeros and replace it with this. And then I can do some bookkeeping and then maintain this invariant. So make sure after the bookkeeping, it's back to having at least one row that's all zeros. Okay, so this is kind of outline of how it works. Let me kind of write down the actual algorithm now. Okay, so first I'm going to say put first 2L minus 1 rows of A in B, right? So I'm going to first put the first 2L minus 1 rows of A into B, and so it's mainly filled, or maybe just the first row of A. You can kind of deal with that. Okay, then I'm going to say for AI in A, so I'm going to cycle through all of the rows of A in like a stream. So this is in stream, and so then I'm going to go through these steps. I'm going to put AI in an empty row of B. So this is one of the all zeros rows that I guaranteed was going to be in there. I'm going to take the SVD of B, U, S, Okay, so I wanted to avoid taking the SVD of A, so I'm taking out B. B is much smaller, so this is going to be done in O of D times L squared times. So this I can do much faster now, it turns out. Okay, I'm going to set and then so I'm going to set delta equals to sigma L squared. This is the Lth singular value of B. So I'm going to take the Lth singular value of B and square it, and this is going to be delta. I'm going to set S prime, so that I'm going to kind of update this singular value matrix to be the diagonal of the square root of the first singular value squared minus delta, the second singular value squared minus delta square root. So sigma L minus 1 squared minus delta square root, and then the rest of these are zeros. And then step 5, I'm going to set B back equals to S prime, this updated S prime matrix times V transpose, which is what I came out of the singular value decomposition up here. Okay. And so actually these rows I do only if no empty rows. So only if I filled up all of my empty rows do I do this step. Okay, so what's going to happen is if I do this, I'm setting a bunch of these equal to 0. So if you remember my singular value decomposition picture, I'm going to have B is going to be equal to, this is U, this is going to be S, and it has more zeros down here, and I'm going to have V transpose. Right, so I had the picture that looked kind of like this, and this step is going to set a bunch of these equal to 0. So I'm going to set a bunch of these equal to 0 if I run this step. And the ones up here, I'm going to shrink these a little bit. I'm shrinking them by this delta value here. So I'm shrinking these, but because these are all zeros, when I multiply by V transpose, here, the last kind of L plus 1 rows are going to be all zeros. So I only need to do this basically every L steps. Okay, so if I go through this, I put an empty row if it's in there. If I filled up all of the empty rows, I take the SVD, I basically zero out the bottom part of the matrix, and I create a bunch of empty rows. Now I've ignored this U matrix because the properties I'm going to guarantee only guarantee stuff about S and V. I'm not going to guarantee anything about U. And I can't really do that because I'm going from N rows only to 2L rows, and U is telling me something about the rows, which I'm kind of compressing all of those anyways. Okay, so I'm keeping a matrix which has roughly the right, the correct right singular values and right singular vectors, and I'm adding rows in until it gets full, and then if it gets full, I figure out what those are again, and I kind of shrink it a little bit. Yeah.
So it seems like after each one of these steps, B is like kind of an incremental SVD of the entire A, but then that means that the rows that you process first in the stream have less of an impact than the rows at the end. So could you adopt like a reservoir sampling like technique and weight the ones at the end more?
Yeah, so if you're doing something random, then reservoir sampling would be the right thing to do. This is deterministic, and there is an algorithm called incremental SVD, which just keeps these singular values the same. It doesn't shrink them. And it has this issue that the rows at the beginning of the stream have more of an effect than the ones at the end of the stream. Okay, and so if you get a lot of mass in a certain direction, then that kind of tends to stick there. I kind of tend to keep my singular values pointed in the same direction. By shrinking them, it's going to have the same kind of trick that I'm kind of doing with the Misha-Gries algorithm, where when I ran out of column of these counters, or these labels, I ran out of labels, I shrunk all of my counters a little bit. I shrunk them all by essentially, I pretended like I added another one and then I shrunk that one down to 0. And this, it biases things to be a little bit smaller, but it ensures that if there's something occurred early and I didn't want to really keep track of it, eventually I will shrink it down to 0. And because if I keep this many, if I keep 1 over epsilon of these counters, I know I can't shrink any counter more than an epsilon fraction of the time, right? So I get epsilon fraction of the total amount of items I see error. And I get a similar effect here. The reason the SVD is important is that it orthogonalizes and I shrink equally along all basis directions. If I just kept the original rows and I just shrunk their norm a little bit, and then if the norm goes below 0, then I get rid of them. The problem is I can have 2 columns that are basically pointed in the same direction. They should be counting for the same singular value composition. If I shrink them both by the same amount, I'm shrinking that direction too much. So I need to do this SVD, which is kind of giving me a basis, a special basis I can shrink on without kind of, it makes sure I don't shrink too much in any one direction. And so that's kind of what's going on here.
So do we have access to the first 2L minus 1 elements of A of the stream?
The other way of thinking about it is I put the first element in the stream, start with B is all zeros.
Oh.
Okay, and then I put the first element in the first location, and then this invariant is not violated until I've seen 2L of the rows. That's also fine. Yeah, but just the first time part through the stream, I always have empty space, so I just fill up my B matrix. Right? If I'm going down like through here, right, and I haven't reached 2L yet, then I can copy A directly over to B. I have no error. Right? It's only once I reach I fill up do I need to kind of do some shrinking stuff.
So the 4 is from I starting from 2L minus 1.
Yeah, yeah. Yeah. Okay, so it looks a little bit like a mess. There are a couple of steps in here, but it's a pretty simple algorithm. And so I'll have you implement this in MATLAB. I gave you a stub of the code. I think I gave you code that kind of does this part and sets up a for loop, and I think you need to fill in this sort of stuff in here. And then you'll run it and see how it works compared to doing the actual SVD. Okay, and so this doesn't do quite as well, right? I can do it with only L rows, and then this invariant happens every time I add a new row, and that's a slower version of it. But otherwise, I need a factor 2 and a factor 1 over epsilon onto the size of the subspace I'm maintaining. Okay, and if I run it with this size, let me just write down the error bounds here. So if I run frequent directions with L equals to K over epsilon rows in B, then I can write down two error guarantees. So the first one is for any unit vector x in in RD, then I can say that I can compare ax squared minus bx squared. All right, so I multiply x, so I'm saying look at some direction, and I want to say how much squared norm is there in that direction x, described in A or described in B. And I know that B is always a shrunken version of A, so I know that this is always going to be greater than 0. So A of x is always going to be greater than B of x. But remember here, I'm always shrinking the singular values, which is capturing the norm of the matrix. Okay? And then I want to say I never shrink it too much. And so I can say that I can compare it to the best rank k. And I can say that this is, the error is compared to the tail. So the sum of the squared singular values that are not in the top k. Right? This term here is going to be equals to j equals to k plus 1 up to d of the squared singular value. So it's the part of the norm not captured in the part that carries the information. So the noise of it, of the matrix, divided by L minus K. So in particular, if you set now L equals to K plus K over epsilon, then this becomes less than 1 minus epsilon so I can get a relative error. I can get up to 1 plus epsilon, right? So up to an extra 10% of the noise in the tail with an extra k over epsilon rows I maintain. Okay, this part here is also equivalent. If you're used to thinking about the covariances of matrix, then so that part is similar to saying that the covariance of the matrices are always close to each other. So I can write down the d by d covariance matrices, and those are always going to be close, if you're used to thinking in those terms. Okay, and then there's a second error guarantee that looks like the projection one from before, that I can essentially, I can define some projection onto the top k. So I can look at the best rank k subspace of B and project A onto that. So this is a rank k, the best rank k projection. And I can say that this is equal to L oh wait, this one only needed to set this, and then this is L over L minus K. And so now if I set L equal to K plus K over epsilon, then this becomes like this. Oh, and this didn't need K. Sorry. Right, so this found K plus I should know this. This is from a paper I had, so. But, you know how it goes. Okay, so you get bounds that depend on relative. So these similar projection bounds that I had here, I get a relative error with the tail, which is this compares favorably to this bound I had with this column selection, where this is k over epsilon squared. Now I'm getting basically k over epsilon, and I get a relative error. This is a little bit slower to run, but the results are empirically kind of significantly better. I would say you need about, often in practice you need about, say, twice the rows of, or twice the number of dimensions of the SVD to approximate this, whereas, or maybe an extra 10 rows to approximate what the SVD is doing, where you need like a factor of 100 rows to do this random projection approach, or the column selection approach. Okay, so any questions about this? I can really quickly. Let me see if I can pull something else up for you while. I covered the technical material I wanted to, but I've got some other slides I can show you that show some empirical results, in case you're interested. So do you think you'd know how to implement this stuff if I were to ask you to implement it? All right, okay. So let's see if this works. All right, so let me show you kind of empirically. This is the error I was showing you before, kind of normalized. So it's kind of, you want it to be closer to 1, means you get as good as the SVD. And so the blue is the norm sampling. The green is some version of these weights which technically are supposed to give you a stronger error bound, but are more complicated to select. So, often these do better than the blue ones, but not in this case. And then you can kind of say deterministically always select the one with the largest score, the column, or select ones kind of, if you do this without replacement instead. So this is the IID reservoir sampling, and this is something more complex that does it without replacement. I could tell you about how to do that. Okay, and then this is the frequent directions algorithm. Okay, so this is this covariance error, which was measuring with respect to any unit vector. And so these are the random projection techniques, the column selection techniques, and this kind of hashing version where you fill that S matrix up with mainly zeros. And they all work roughly the same. This is the error you get with the SVD, and this is with the frequent directions algorithm. So it's not doing quite as good, but if your goal is to get 50 dimensions, you're going to do about as well as if you did 25 in this particular data set. And this is returning all zeros. So these randomized approaches are nice in that they're easier to implement, they're faster to implement. But until you get to about 100 things you've selected, they don't even break even. They're adding bias to it in weird ways. So this all zeros actually did better. And eventually they start doing better. See, and then this is this projection error, where we're looking at how well you capture the subspaces. Again, the frequent directions is basically matching SVD, where these other ones are doing worse, but the all zeros is no longer like it's beating that immediately, which is not surprising. And this is the speed. An issue is that these frequent directions based ones are a bit slower. This is a way to do a little bit. It's a way to do it. The yellow one and the gray one are one where you use 2 L rows instead of L rows. These are using only L rows. So every step you need to call an SVD. You can see these are running significantly slower. It scales quadratically with the number of rows that you keep, where these scale linearly with the number of rows. And these are all the random projection techniques. You can make them much, much faster. It's basically as fast as reading the data. Or the column selection ones, you can make those pretty fast. If you compare the error versus the runtime, you can see that these are kind of the best of the randomized approaches. This is the algorithm I described to you, the norm sampling. And there are ones that are a little bit faster to implement, that you can run them so you get a subspace of size 5,000 down here. And this is better than, I think it had started with 60,000 rows. So I went from 60,000 down to 5,000, and of course I got a fairly small error, and you can do this really fast. And these are the frequent directions algorithms, and they get roughly the same error of size 20 instead of size 5,000. But the running time is more, right? These are super fast, and these take longer. Okay. Okay. Oh, I thought of something else cool I can tell you. So, all right. So one of the things you saw on there was instead of like the reservoir sampling, right? You asked this question. This sampled stuff. This is sampled in IID, right? So that means I have to, if I want to maintain 10 or 100 or 500 of these samples, I need to do these independently, which means that if I want to do this with the weights, proportional to the weights, and some of the rows I want to keep because they have a really large weight, I'm going to tend to sample those over and over again. Right? So there's versions of this where you want to sample stuff instead, so you never sample something twice. Right? So I never sample something twice. So there's a really cool trick how to do this called priority sampling. Okay? And so what I'm going to do is I'm going to so again I'm going to have the stream A1, A2, and for now, and these have weights. And for now, forget about the stream. Okay, and I'm going to create instead what's called a I'm gonna create what's called a priority, a row I, row 2, up to row n. And so row I is going to be the weight I divided by ui, where ui is going to be uniform between 0 and 1. Okay, so now the priority is a random value. It's going to be larger if the weight is larger, on average. But if I happen to pick a really small uniform random value, like 0.001, then I'm dividing by that, and this is going to be really large. Okay, so I might pick really small things, but not usually. Okay? Now, and I can assign these priorities as I go in the stream. And now I want to keep the top k of these priorities. So the top k priority weights. So 1 prime. Right, so if instead of sampling k independently, I can pick these, and I can just use now a priority queue. And you probably have learned about like queues in like a data structure class, right? And how to do these efficiently. Technically, they take log n time if you use like Fibonacci heaps and so forth. You can implement them pretty efficiently. You only need to maintain the top k part of this. And so this takes log k updates. You can think of maintaining like a balanced binary tree over the what's the right way to implement this? But you can maintain a priority queue over these weights, and you only need to maintain the top k of them, and you can do this efficiently. I guess you can amortize it, I think, to be constant, close to constant time. I'm blanking on this now, but you can maintain these instead. And this is a cool way to keep weighted items in a stream, and this works without replacement. And so this magically, this is also going to be unbiased. There's some cool properties about this priority sampling. There's something called variance optimal sampling, which is like a shade better than this, but in practice it doesn't make a difference. So if you want to maintain things in a stream with weights without replacement, so you don't keep things twice, and this is a cool way of doing it. All right, cool. So I'll stop here. We'll start on some new stuff next week on Monday. Well, so you want to have the things that have a small weight. You sometimes still want to pick those in case